Morning, everyone. Hopefully, everyone had a nice weekend. I apologize again for not being able to be on the lecture live and in person on Friday, but we'll get back at it here again today. Today, we're going to transition from talking about volcanic hazards, mainly related to volcanic hazards, and other hazards like earthquakes and tsunamis, mainly related to plate boundaries, and we're going to talk about oceanic and coastal processes. Part of this is going to be just kind of informing you about what these oceanic and coastal processes are, getting you aware of the key concepts, and then I'm going to talk a bit about both hazards and also not just hazards, but just sort of the processes that influence how society interacts with the coasts. This is a major issue. A disproportionate number of humans live near major coastlines, and as a result, live their lives aware of and influenced by oceanic and coastal processes. Just like set the tone for this lecture, just like all the other many other factors we mentioned, like water use, energy use, population growth. The number of people living near oceanics or near the coastlines is increasing dramatically. Even relative to the growing population on planet Earth as well. So from a sustainability perspective, people are disproportionately moving towards the coastlines, and as a result, particularly in developing nations, there is a disproportionate amount of people who are living, at risk of being affected by various coastal processes. So this is actually a picture of an incredibly large wave, and don't worry, this is intentional. There's an individual surfing on this, and this is actually at the in Portugal, the Nazaire surfing challenge. This is an area known for incredibly large waves, and people actually intentionally go there and put themselves in harm's way by taking advantage of the coastal processes we'll talk about for some fun and excitement. So what we're going to do for at least first today and Wednesday, probably most of this week, is take you through the key aspects of oceanic and coastal processes and how they influence society and how we've influenced the rate at which these processes occur. So you can get the perspective here. This is I think a 3-story building with a light tower, and that's some of the largest waves you find anywhere in the world at Nazaire. So a key thing here, and some of these topics have sort of already been introduced in terms of talking about tsunamis, but we're gonna talk about waves and their characteristics. So we're gonna push into that a little bit more. That will be some of this will be familiar to you, but some of it will be new from that perspective of understanding oceanic waves. The other thing we're going to talk about a lot is that even though we don't see it as sort of an obvious big hazard like an earthquake or a volcanic eruption, coastal erosion or the erosion of coastlines. This is not just on the oceans, even in the Great Lakes as well, is actually an area of sustainability that's of greatest concern to coastal communities and also to the health of aquatic ecosystems near coastlines. So this is a topic that's a major issue. Humans have influenced this in a profound way, both through human activities, such as putting in pipelines and stuff like that, changing vegetation, but also based on the fact that climate change has caused the sea level to rise, and those sea level rises have exacerbated the rates of erosion quite dramatically. And then the next component we'll talk about, although these are not obviously tied directly to humans, is just going through the hazards tied to cyclone formation. So in the East Coast and the Atlantic Ocean, these are called hurricanes. The West Coast, these are called typhoons. But globally, everyone collectively calls them cyclones, and we're going to talk a bit about how those form, how they move in the ocean. In the global oceans, and how they can obviously have some pretty devastating effects on society. I think many of you are probably quite well aware of the influence that cyclones, hurricanes, typhoons can have on people, having watched the news in the last few decades. But like the other things, it's a point of reference to recognize that, simply put, having more people living in coastlines makes the potential impacts of each of these things significantly greater than they were in the past, even on a numbers, but on a percentage basis. We're also going to talk about the upwelling in coastal regions. This is actually where deep ocean water, particularly deep, cold, nutrient-rich ocean water, can actually migrate up near coastlines, depending on the waves and temperatures of the surface oceans. And clearly, those things vary throughout time, are really important to global markets such as fishing, um, global temperatures, and also it's an area where we've observed that humans are, causing some influence in global climate change has caused an influence on changing these global cycles. So we're going to make you aware of them so you can, as your life unfolds and climate change becomes more and more of a reality, you can probably make informed decisions about how that's going to in fact affect climate, weather, and things like that. So where we're going to start out is just giving you some perspective on how important coastlines are to a country like the United States. The U.S. contains about 93,000 miles of coastline, including the Great Lakes. So you can imagine that's a fairly large amount of coastline that's has to be watched, has to be monitored, and where people are always endlessly trying to live on an increasingly great percent. Um, so all those have the potential to be influenced by coastal hazards. It's an area that a coastal, oceanic and coastal processes don't get as much attention in a lot of environmental science classes per se, but have one of the most areas with the most vast potential to actually influence society. Um, Along those 93,000 miles of coastlines, approximately 75% of all the people um, living in the United States live in these coastal states. Not all of them live, on the coast. Not all of them live within, an obvious, area where the tsunami is going to influence them. For example, not all of them live within 10 miles of the coast per se, where routine tsunamis, if you will, would influence them. But the vast majority of people obviously clearly live in coastal states, and as a result, there can be significant influences, in terms of things like cyclones, hurricanes, or typhoons that can influence these populations in a devastating amount. And also, what we're going to talk about a bit throughout the course, or throughout the lecture, is that also the decisions made upstream in these coastal states, particularly, can have a great influence on the processes that occur near the coastlines. So, this means that by necessity, the vast majority of people are impacted by coastal processes. And for perspective, I already alluded to this, but I think it's worth reiterating is that from the perspective of sustainability, the hazards associated with coastal living and the influence that coastal living has on the oceanic and coastal processes will only increase in the 21st century, particularly in light of sea level rise and changing climate. So when you think about this from a hazards perspective, the most serious hazards related to coastlines include the generation of riptides in the surf zone. This isn't just everyone's aware of the fact that riptides, where water comes on shore and leaves in a channeled area, can be really fast moving currents and can cause a lot of risks, a lot of hazards to people who are sort of surfing and playing in the water. If you've been to the beach, you've seen the flags going up for potential for rip currents in a certain area and stuff like that. And these can be monitored with satellites and with from the beach or from helicopters, stuff like that. And they do present a hazard to surfers and swimmers alike. Well, what's actually the reason they're so important to coastal hazards is not just the great risks of drowning or things like that. Is that they can also do a lot of localized property damage to boats, and things and such. But the biggest issue is that they cause very channelized local erosion pathways where the beach and the channels and the sandbars can be wiped away in a certain area where rip currents form. And once that happens, that becomes a preferential pathway for more rip currents, and you can really devastate the sandbars and beaches in localized areas. Generally speaking, one of the problems, not just because of global warming, but certainly it's been exacerbated by that, is the issues of coastal erosion. Most of our beaches today on the East Coast are experiencing large-scale erosion and basically beach loss. Many of the beaches are managed beaches where people are actually taking sand and spreading it out each day to try to keep it in a little channelized area. The dunes, for those of you who've been to areas like the Outer Banks or something like that and see the great sand dunes, they're being eroded relatively rapidly. That's along all the East Coast. They're being eroded very, very rapidly. And as a result, coastal erosion, not just for the fact that properties are now, that used to be back of the dunes or away from the water, are now actually in close proximity and in being influenced by ways like that. It's really changed the way the coastlines look. So much so that today in the United States and throughout most of the rest of the world, sand, just simply the ground up rock, but that is largely quartz grains and feldspar grains, stuff like that, and carbonate grains. Sand is actually now considered a critical resource because there's so little of it around. Partly because people are trying to rehabilitate coastal communities, sand dunes, and beaches, and also because it's used as a valuable building material in a lot of different areas. So um, this has become a major issue where the erosion of this material has caused economic and the local risks. Obviously, we talked about this before, and I won't go back into it very much. Tsunamis are a major coastal hazard associated with coastal and oceanic processes, and of course, tropical cyclones, the occurrence of hurricanes, typhoons, have potential to do devastating damage. No surprise now, things like Hurricane Sandy, even going back to Hurricane Andrew in the 1990s, that can do billions and billions of dollars of damage and completely devastate economies of areas, let alone lead to great losses of infrastructure and human life. So we're going to start now is just kind of go through the basics of the coastal processes. The key one here, which has already been introduced a bit in terms of tsunamis, is waves. So there's two coastal processes people kind of confuse and get mixed up. But tides are caused by the gravitational shifts of the moon rotates around the Earth. But waves are really those sort of have almost 2 high tides, 2 low tides a day, about 6 hours and 13 minutes apart. So they move each time throughout the day. But waves are really, but tides are fairly predictable. We know those very well. There can be high and low tides in all parts of the world, and certainly in areas like Newfoundland and Nova Scotia, there's narrow channels. Tides can cause great increases and decreases in coastal water levels. But the reality is, in almost all parts of the world, tides are pretty well constrained and don't influence, don't present major environmental hazards, or they're geologically well understood where in different geographic areas. But waves, on the other hand, actually can have a pretty profound influence. So what we're going to do is talk about what actually causes waves to be formed. Obviously, the example I won't discuss here is something like an earthquake causing a major displacement of water, like a tsunami or a volcanic eruption or a landslide or meteorite impact. All those things can cause the energy up or down to displace the water and lead to a wave being formed. So certainly those are processes, but obviously most of the waves we experience on planet Earth or on the surface of the Earth are not related to tsunami events in any of those forms. So the key thing here is that most of the waves are actually formed by offshore storms. Anytime there's an offshore wind pattern, which is typically are driven by atmospheric pressure displacements caused by storm events, where you have a low pressure system related to the evaporation of large amounts of water, they're the processes that ultimately drive wind patterns, drive the weather, and also drive the waves. And what happens is that the wind that blows over the surface of the water actually causes a frictional plane between the air and the wind boundary, and that causes the water to become turbulent, creates a directionality related to the wind that's flowing, and causes the water flow in a given area. Now, in the coastal areas, there are sort of two major components of this, where the wind blowing causes this. There's the storm processes that are abundant out in the ocean, all over the world, where storms are moving around, causing wind to blow and causing ocean waves to be generated. And there's also sort of the daily constant heat near the surface ocean boundary, where the land heats up during the day, creates a high pressure system, causes the wind to blow offshore, and then at night, when the water's warmer than the land, where you see the process sort of reverting back. So there's also localized wave patterns that are exacerbated on top of these sort of grand offshore storms. But in all cases, and we're going to stick with the storms as an example, it drives most of the winds, large-scale waves. Wind drives most of the large-scale waves across the ocean, resulting in the fact that air is simply moving faster than the water, and as a result of that frictional plane, the energy is transformed from the air to the water and generates these waves. So in all cases, independent of whether it's generated by the wind, which type of wind or other processes, the size of the wave depends on a number of factors. Particularly, the waves depend on the velocity or the speed of the wind. So how obviously think it would sort of be common sense to most of us at this stage in our lives. The wind goes faster, the waves can get bigger, and can actually occur more rapidly, which we'll get to in a second. Um, the duration of the wind, if the wind blows for 1 second versus blows continuously for for long periods of times, that obviously can cause the waves to that transfer of energy from the air to the wave can be sustained and create longer, larger waves. The third, which hopefully many of you have heard this word, but if not, it'll introduce a new term, is that the length of the total distance, the length scale which the wind blows across the surface, is called the fetch. And those three factors, the velocity, how continuous the wind blows, and the total distance or fetch at which that wind blows, all dictate the size of the waves, and we'll talk about that specifically here in a moment. So there's a couple of key parameters of waves, some of which we've talked about in the tsunami discussion, some of which will be new here. But in reality, each of these are sort of important and relevant to know. If you're ever out on a boat or fishing vessel touring around, you often hear on the intercom that people talk about these particular factors. So here in this situation, we're going to model this and define it all, assuming the wind is blowing from right to left across your screen. Okay, and in that scenario, what that means is that the waves are going to be generated, in this direction as well. The energy is transferred in the direction it's going. Okay, and the key terms to recognize here is that the wave height is going to be the distance between the crest, or the very top of the wave, and the trough, the bottom of the wave. So the wave height, again, is going to be the distance between the crest of the top, the trough, or the bottom of the wave. So obviously that means that the crest is defined as the maximum height of the wave. The trough is defined as the wave base, or the bottom of the wave. And effectively, the wavelength is the linear distance between one crest and another crest. Now, typically, this isn't done by trying to look at two places at the same time. It's actually done by monitoring where a crest crosses one point, letting the next wave come in, and calculating the time and the travel distance between that next crest arriving to define the wavelength. And for perspective, that those crests, multiple crests passing a specific reference point, typical periods are around 5 to 10 seconds, and this produces wavelengths, typically in 39 to 156 meters. That's in typical wave patterns in the ocean. Oftentimes, when if you've been to the beach recently, probably this year, maybe that can happen. But you see the wave coming up, you see a pattern, you see the wave go up again. It may not seem quite as long as that, but I always thought these numbers seemed a little bit long. But the typical wave pattern is about 40 to 156 meters, and typically it's closer to about 100 meters in between each wave. And you can actually calculate the wave velocity by measuring the distance between two successive crests and the amount of time that's elapsed between there, and that'll give you a wave velocity, or basically how rapidly this all this is occurring. Key thing here is obviously stronger, higher velocities of waves will lead to higher velocity of wind. Will lead to higher waves and a shortened length between crests, or a faster wave velocity. Increased duration of wind doesn't necessarily change the velocity as much, but decreases the distance between decreases the wavelength, and also increases the height of the wave. And specifically, a longer and longer fetch will often increase the height of the wave, but doesn't actually necessarily change the wavelength as much. You don't need to know those nuances, but just you can think through that sort of logically in terms of how each of those would affect those processes. Much like the case of tsunamis, as looking at this in the global ocean, the wave height will be the distance between the trough here and the crest, and the wavelength will be the distance between two different crests. There's nothing mathematically different about doing the distance between two different troughs. It's just obviously easier to see crests in a given pattern. Again, these can be monitored by satellites, by more commonly by helicopters and things like that, or simply people working in lighthouses if they find this for a long time. The process is the same. I understood that there's actually a sort of an incorrect problem in the quiz last time, and I apologize for that. It's been corrected, and don't worry if everyone will be given full credit for that question. But the key aspect here is that the wave velocity decreases as you get closer to the shore. Basically, it's a mass conservation of mass problem. The material in the open ocean can be moved really rapidly across the ocean, but as you get to a progressively shallower and shallower coastline, that energy has to slow down, and that energy is transferred to a vertical profile of the wave. So, a good rule of thumb is that the wave height in the global ocean will at least be two, sometimes even more higher than the actual height of the wave height out in the open ocean. So as a result, again, as the wave, again, the question on the quiz last time, I realized it was a wrong answer recorded, and I fixed that. But the key thing I want to reiterate here is as the wave gets closer to the coastline, the wave velocity slows and is transferred to building a higher wave, which can often break onto the coastline here. Some other key parameters here, in addition to the wave height increasing at least by a factor of 2, sometimes larger, and depending on the velocity. So the faster the waves are coming in, the more they have to slow in a shorter period of time. The higher the waves, slower waves, baseline about 2 times increase in heights, very normal. In situations like tsunamis, for example, or major, cyclones, it can be larger. And basically, the period where the location between the coastline and the open ocean, where you start to see these waves build height, where the velocity slows and height increases, is what we call the surf zone. It should be fairly easy for y'all to remember because it's where you go surfing, right? And then the distance very close, where the height of the wave can no longer be supported by the amount of water underneath it, is where the wave causes the waves to just basically lose momentum and break. And that we'll go through the different types of waves here in a second. But the locations where that waves start to top off and break, the waves themselves are called breakers, and we'll talk about the different types of those. But the area between the coast, or even on what you call the beach, but on the margin of the beach out to the surf zone, it's called the swash zone. And this is where it's just total chaos. You've all seen it with those frothy white water coming in and out and moving around, and effectively, these are the regions where most of us would experience the ocean going swimming, having water come out and slosh around with us. So we'll talk a little bit more of these processes in a second. So the sets of waves that are basically generated far out in the ocean are called swell. So when I talked about the fact that most of the waves in the ocean are caused by storm events, those distant storm events that cause the waves to sort of be generated, the storms generate wind, which are transferred towards the coastlines, generate waves. That's called a swell. So typically in most marine discussions, swells are used to talk about areas of high standing waves, or when you have a greater wave heights or greater velocities than normal. But actually, that by definition, the swell just defines how much wave groups are generated. There's often sets to these waves. I've heard different people say 7 or 11 sets in a wave. I don't know much about that, to be honest with you. The key thing here is, again, when waves reach the coastline, they expend their energy in a pretty significant amount, where the velocity decreases and the height increases. So for perspective, just give you just how much energy is generated along a 250-mile length of coast in an ambient swell, not during a hurricane or typhoon or anything like that. Waves of a 1 meter wave height out in the open ocean will expend the equivalent to power produced by a nuclear reactor over the same period of time. So that means daily, your calm average, sort of the background swell generates about as much as a nuclear power plant, over a 250-mile length coastline. Obviously, if you think about the fact that we have 93,000 miles of coastline, that's a pretty big number if you consider the fact that if you could ever devise technology that would allow all that energy transferred to power, for example. So the key thing here with energy is the amount of energy gained by the wave is approximately proportional to the square of the wave height. So a 1 meter, key thing here is a 1 meter high wave would generate one squared is 1 watt meters. If you actually have a 2 meter wave, that's 2 squared, so it's about 4 times more powerful for every doubling of the power energy that's generated by those waveforms. Okay, so 4 times higher amount of energy derived uh, by a wave that's 2 meters in height. If you think about this in terms of actual storms, during not even necessarily a hurricane, we might see waves of 5 meters when there's a near shore coastal storm, and that can lead to 25 times more power generated along the coastline over that same unit of distance. Okay, so there are different ideas. Most of these have been deployed in off the shore of Southeast Asia or in the North Sea, are both areas where actually there are relatively high basal swells, wave energies, where people have tried to moor down to the seabed these apparatus and basically utilize the flowing energy coming back and forth past the units to try to generate power. And there are a few test things like this. There's some optimism that long term they can provide some basis of energy storage, or energy, not storage, but energy generation. Excuse me. But I have to say that these are major expensive infrastructure costs. They're certainly a component of these that people get excited about because they don't use fossil fuels. But from perspective, there's a lot of energy, particularly fossil fuels, generated to make the steel for these really large apparatus. Secondarily, the energy has to be transported or transmitted more accurately from these power generating stations back to the shorelines. And most importantly, there's also concerns about the fact that you could cause local ecosystem damage in these oceanic areas by siting these things there. Clearly, if it can ever be harnessed, there's a lot of value in doing so, but I want to make you aware of it as a new idea in harnessing the immense power of these waves. So there's optimism for the future, but there's also a lot of concern that there'd be, issues with ecosystems issues related to this. My perspective is that, in your generation or maybe your children's generation, we might find out more. Clearly, this compared to the questions of ecosystem damage compared to something like the Macondo blowout in the Gulf of Mexico in 2010, you have to start thinking, well, we might have damage, but we can predict that a little bit more accurately than we can from some of the accidents. So there's potential for this to be used and harnessed for wave power, but for most of my lifetime, it's been an idea, and there's been a little bit of advancement in terms of trials and simulations, but no clear pathway yet that people have identified. So just to sort of put this together again, key aspects here: wavelength, or distance between two waves, the crest of two waves. Crest and troughs are the highs and the lows, respectively. Wave height is the distance between those two. Remember, most of this is basically a movement of energy driven by wind. And I guess so I won't spend too much time on this, but I'll make you aware of is that this wind, in addition to causing waves in the water, actually does a lot for distributing nutrients and causing mixing in the tidals in the top of the oceanic zone, and particularly in tidal zones, which it distributes nutrients around and actually allows distributes nutrients, allows the top in the open ocean up to 200 to 300 meters of the open ocean actually be what's in the photic zone, where solar radiation can penetrate into the water and actually stimulate photosynthetic life in the top part of the photic zone. Without the waveform mixing, most of these particles would just sort of be up near the top, and all the photosynthetic generation would be very narrowly around. So waves are pretty important for a lot of different things, particularly as you get into the surf zone, or from the surf zone within these. Excuse me. The waves, particularly the breaker waves, cause major mixing of nutrients. As you get close to the shorelines, that's important for the sort of the photosynthetic life cycle near those areas, and also for creating a little bit of motion to get particles, material deposited. So if you want to think about things like oil and gas formations that are in the subsurface that are targeted for oil and gas generation, these rely upon things like shales being deposited in deep water in the geological past, where these materials are only transported down based on the fact there's enough waveforms of material that causes this process to go forth. Importantly, and which leads much more directly to the hazards we'll see from coastal processes, is that this sort of mixing in currents are mini currents developed by the particles in water motion delivered by the transfer of, by the waves, particularly as the energy is transferred as the wave slows down. That turbulence causes major opportunities for coastal erosion and even beach erosion and dune erosion, et cetera, all encompassing there. So key things again: waves decrease, wave velocity decreases. I've said that a few times. I'm overemphasizing that based upon the problem with the quiz. But the key aspect of determining when a wave will break is that as wave height increases, waves are unstable or unsustainable once the height is greater than 10% of the wave length. So if a wave length is 100 meters, which is not at all abnormal, that means you can only get a 10-meter wave before the wave becomes unstable and breaks. For those of you who've been to if you remember being to the beach recently or even as a child, you ever standing at the beach, standing on a little sandbar and watching the waves come in, the waves that actually hit you the biggest near the coast are often not the ones you see the highest waves out deeper. And oftentimes you see the waves that are a little bit deeper and are pretty high, they'll break off well up before you get there. And that's exactly this phenomenon, that it has to be about 10% of the wave length, or else it'll become unsustainable and break. So each of these waves, obviously the potential for erosion and damage depends upon a variety of things, particularly the wave height and the short wavelength. The bigger the height, the more frequent they occur. It can cause more turbulence and more erosion. But generally speaking, we sort of break these down into two main types of waves. There's what's something called a plunging breaker or plunging wave, or a spilling breaker. And basically, the plunging breaker are ones where the wave height exceeds the 10% of the wavelength and causes a massive crash down of water. Obviously, you can guess here, these are really fun for surfing in, but these plunging breakers can basically transmit a lot of energy onto the beach and cause massive amounts of beach erosion. In general, spilling breakers that sort of just spill out are a little bit more fun for, look a little bit more like this. This picture is actually from the Outer Banks. And you can see these are a little bit more fun for sort of standing in the surf and letting the water roll onto you, but aren't great for surfing. More importantly, these don't often lead to major erosion events. And, you're seeing a transition now as water levels have increased, but for most of the history of the Outer Banks in the last 10,000 years, these spilling breakers can actually transmit sand and debris back to the beach and actually increase the length of the beach. Last several hundreds of years, there's more of a transition to plunging breakers, so it's being eroded away. But part of this is tied to the actual coastal geology. The shallower and flatter the coastal profile, the more likely it is to experience less erosion. Obviously, having something like a sandbar or something out here that prevents the erosion from happening, near shore is an important aspect of that as well. But more commonly in steeply sloping, beach terrain, you're more prone to having plunging breakers and can also experience great amounts of erosion. So I'm not responsible for the music for this. I'll preemptively tell you, but this will give you a sense of the sort of the big waves in turn that down just a little bit. The music is a little too loud. Right back. So I apologize first for the music if that was I didn't choose it. But gives you a perspective of just how big these waves can be. So I thought this is from Nazare or Nakare, probably I think I said Nakare before, Nazare, Portugal, and this is on obviously the west coast of Europe in the Iberian Peninsula there um, along the Spain and then Portugal. And the reason the waves are there are so large is the same processes that occur transferring waves into any other coastline, except for, as I mentioned earlier, as the waves get closer to the shore, they have to slow down, transmitting their energy upward, making larger waves. It's the same phenomenon, except for there's actually a channel here near Nazare, where that channel causes the waves not just to have a mass conservation issue in terms of getting closer to the shore, but also as it gets closer to shore, it gets channeled in. And that narrowing of that channel causes all that water to have to displace its energy upward and leads to some very predictably large waves. Of course, tied to the idea and introducing the idea of coastal erosion, which we're going to get to here in a moment, it's actually problematic for the long-term viability of the area, right? That channel that's formed by a past episode of erosion that's caused debris to be removed from that area actually means that the more energy that's brought in a narrow channel has to come right back out of that narrow channel. As a result, the channel gets deeper and deeper and deeper, effectively creating potential for greater wave volumes in that area, but also means that there's not a lot of coastal mixing and there's very intense erosion in that area. So these can lead to long term can lead to some channels that are quite deep in localized areas. And more broadly, even though the examples are not nearly as extreme as the channel I show you at Nazare, is the issue of the fact that the coastal erosion is one of the biggest issues facing society today, period. These are an example from the Gulf Coast, and as a result of the fact that normally the Mississippi River brings a lot of material, debris, silt, sand, and soil. And what typically would happen is that this delta would basically come down, be very rich in muddy water, and as it got to the ocean interface, what happens is the amount of water coming down stays relatively constant, but the vertical profile as you get close to the ocean slows. The water starts to slow down. As the velocity of the water starts to slow down, the sand and heavier grains start to become too heavy for the water. It's something called Stokes settling velocity, where the velocity of the water can carry bigger and bigger particles, increasing velocity. Once that water slows down, the bigger particles start to fall out of the water column. And actually, typically in most deltaic environments, you actually have a prograding delta. The delta is getting bigger, more material is getting deposited, and the coastline is getting both extending out into the ocean, but also protecting the coastline more and more. Second factor is that as the fresh water hits the salt water, there's a phenomenon called flocculation, where the salinity of that ocean water actually causes the particles to get pushed closer together and increases the likelihood of being deposited. So the normal setting, a place like New Orleans for the last thousands of years, has been that material's been rushing out of the Mississippi River, and the area of New Orleans has been basically increasingly extending out into the Gulf of Mexico. Sediments are getting buried and packed deeper and deeper and deeper, and the coastline is being protected. However, if we sort of stop the balance between those two phenomena, we can actually experience coastal erosion. This is, New Orleans is a perfect example of this, but so is basically most of the coastlines in the world. Okay, so I'll give you a perspective here in the Gulf of Mexico near New Orleans today. The balance of material getting down based upon a variety of different land use changes, coastal engineering, the way we've put up dams and things like that, is that the load of sediment's not in balance any longer, and as a result, a football field-sized piece of land is washed away every hour from the end of the delta here in the Gulf of Mexico. And as a result, you're seeing major episodes of coastal erosion, where there's no longer material prograding out into the Gulf, but also it's sort of slowly chipping away and driving the coastline back further and further towards the city. Obviously, this can have a lot of implications, but one of the most important is that the coastline is no longer extended out into the ocean. As a result, those sort of breaker islands, as some people call them, where the land masses take up a lot of those waves, dissipate a lot of the wave energy, but it doesn't really matter because more sediments are coming in to fill it in, are lost. And once that's lost, you get those waves coming closer and closer, and erosion driving back towards New Orleans or other urban coastal areas more broadly. So all those are concerns. You have to recognize that erosion is no longer there. It can't protect us from what's occurring. The example of the Gulf of Mexico near New Orleans is one example, but this is true of all the coastline of Texas, North Carolina, et cetera, where this is a major concern today. So for perspective, in coastal Texas, human modification of the coastline, doing things like building in seaways to bring goods into market, pipelines, is thought to accelerate erosion by 30 to 6% over the last 100 years. And in those cases, pipeline installation, upstream trapping of sediments, many times accidentally by flood control measures or dams to create irrigation channels or to create, get water for reservoirs for drinking water. Those actually cause a lot of the sediments that would lead to prograding deltas going deeper to actually become sediment starved and cause a great potential for erosion of those deltas then over time. As a result, and not blaming the situation of Hurricane Katrina or Hurricane Harvey in New Orleans and Houston, respectively, on these processes, but clearly, in the absence of these types of breaker islands out deeper in the ocean, you can recognize that there's going to be a greater potential for those hurricanes or even major the beach erosion to get pushed further and further and closer to the city where the damage could be greater. So not implying there's a cause there, but clearly as we keep going down this path of having greater amounts of erosion, starving the sediments, and not allowing the deltas to be there to protect us from these major storm events, there is a greater potential for increased damage from hurricanes to move forward. Another factor of this is that the transport of these sediments to the ends of the deltas lead to more landmass. That landmass eventually gets precipitation that falls on top of it from rainwater, which is fresh. And that fresh water flows through the subsurface of the ground in these deltas, and that actually, by increasing the hydraulic head, putting more water up in there, pushing down, it actually eventually flushes salt water out of the sediments and creates basically freshwater aquifers out in this material along the margins of the Gulf. That fresh water is important for a lot of reasons. One, we can actually use it as a drinking water source. We can use it for irrigation. We can use it for other sanitation, hygiene related aspects of freshwater usage. The other is the fact that when you actually start pumping that water, and this happens all along coastal communities everywhere. We'll talk about this more in the lecture on Wednesday. You can see something called seawater intrusion. Once the hydraulic head's no longer pushing less dense fresh water down, the more dense salt water sort of fills in the gap, and it's called saltwater intrusion. Well, if you're in a scenario like this where the erosion's removing the coastlines, it makes it really hard for the freshwater hydraulic head to build up, and as a result, the saline waters can sort of intrude. And once that happens, you're talking extended periods of time beyond the human lifetime cycles for that fresh water to get pumped back out and sort of remove the salinity. So as a result, in addition to pipeline installation, upstream trapping of sediments, saltwater intrusion, and also just devegetation of the coastlines, you're seeing major erosion of events that are actually increasing much more rapidly than they ever have in the past. So this is just a perspective on the implications of coastline loss. This is looking specifically at Louisiana, and this just gives you the percentage of land below sea level by parish through 2100. So if you look here, the red bars are what's actually really happened by 2010. The blue bars are what's projected to happen by 2050, and the green bars are what's projected to happen by 2100. But this will give you a perspective. Lafayette, currently there are no bayous, if you will, nothing below land sea level, and that's not projected to change. But that's pretty far inland. I don't think it's on the map, but yeah, Lafayette's back up in here off the map. And then places like Orleans, right near the coast, today about 54% of the land surface is actually um, below uh, sea level, but that's supposed to get up into the high 80s by 2100, and even within next 30 years, you're going to see about 20 some percent increase of sea level. Right, and it might not sound like a huge number, but when you recognize the amount of damage caused by Hurricane Katrina, the amount of area that was inundated by water, some of which is actually remains inundated by water, if you didn't know that, and you think about expanding that 20%, in light of the fact that the population of the city is actually increasing, that the population density is increasing. It may be that this happens slowly and we relocate people, but what the fear here is that there's more commonly a major storm event that causes an inundation of an area, and then can cause pretty devastating amounts of damage. So you can see here a place like Louisiana, simply by starving the sediments, transport down the Mississippi River, creating clean open channels for transportation and other things like that, have irreparably changed the amount of material that's going to get to the coastlines to have the deltas be stabilized or to increase mass, which is what is a natural process. Instead, erosion is causing seawater to come back the other way and inundate in those areas. So the long-term forecast for places like parishes are the equivalent of counties in Ohio. For places like Orleans parish or county equivalent, you're going to see, in the next, 80 years, about a 30% increase of 30% of the county is going to be taken from land masses where people are living, or there's natural ecosystems that are going to be transferred to basically being below seawater bayous and swamps, based on the fact that this coastal erosion is happening out further along the delta than even where they're located. So, of course, just for clarity, those numbers are based on sea level predictions of about 1.5, 4.5 feet over that time frame. Clearly, those numbers could be, as you know, could be less or more. They're thought to be a pretty reliable range. But for perspective, you've seen this process over the first 10 years into this 2010 to 2050. We've seen this process occur, pretty predictably and continuously so far. So, in that area, Louisiana, because of the fact that it's a low-lying coastline, you would expect to see the vast majority of this. And in light of the fact that the sediments that are present in the bayou will actually continue to sink on their own, it's not believed to be unreasonable to experience about 4 to 5 feet local, relative sea level rise just from the settling of those sediments in the absence of more sediments coming in. So, it's two competing factors here. If I haven't reiterated this clearly, climate change is happening. Sea levels are rising. We're observing that consistently over the last, dozens of, few decades, whatnot. But the other factor is locally is that without the sediments sort of, here is a place where the sediments are coming in and kind of, balance that increase in sea level to a certain extent. But obviously now, as we've starved sediments from those areas, we've sort of irreparably changed the direction of that for the time being. So, some new land is being generated. There are locations where sediments are actually, increasingly coming out, and there are permitting areas in certain locations. This is at the mouth of the Wax Lake and the Atchafalaya River, and some of the areas are actually seeing sediments increasing. This is 1984. This is 2014, where there's actually are some areas of localized prograding sediments. So the question here is, if anyone's wondering, is why does sediment accumulate here but not in the mouth of Mississippi? Why is it that we have not? Why is it that certain deltas are still prograding and actually protecting the land masses, but others are still seeing rapid erosion? I'll give a second in case anybody wants to take a guess at this, why the phenomenon is happening differentially in certain areas. So the main reason here is largely due to channel control. Okay, the reason that some of the areas are actually being, acting as they normally would have, is there's no longer dredging of channels in those areas to allow major seagoing vessels to migrate up and down them, tourism, etc. A lot of it has to do with the fact that these are sort of rural agricultural areas. The seaways are running a bit more naturally, and as a result, the sediments are actually being transported down as opposed to areas where there's, they're managing the channel, keeping it void of sediments and keeping an open pathway for transportation. And as a result, these areas are going to continue to expand. But I want to call your attention to one component of this, which is the notice these breaker islands. Those are just little blips in the imagination that are there, sort of getting above surface water. Each of these actually contributes to preventing coastal erosion. And then I think what I'm going to do here, since we're already at 10 o'clock, I'm going to pick up with cyclones on Wednesday. I'm gonna end here, pick up with cyclones on Wednesday. Does anyone have any questions? Just a reminder: a week from Friday is our next midterm. Everyone did really well in the first one. I don't expect anything different in the next round. Everyone will do well, but a week from today, I'll post a review for the second midterm, much the same as the first one. So keep doing well. And then on Wednesday, I'll pick up with cyclones, aka typhoons and hurricanes, and we'll go from there on Wednesday. Again, I apologize for not being able to do the lecture live on Friday, but thank you for being patient. I hope everyone has a good week.